Hello, good morning, good evening, afternoon, whatever time it is when you watch this. My name is Raj Rai. I'm going to be presenting my work as well as Qualtech Systems Inc.'s works on digital twins, AI systems for creating digital twins, and things along those lines. So this work was sponsored by the Air Force under an SBIR Phase 1 research contract. And generally speaking, our goal was to expand on existing technologies that QSI already commercialized. And to kind of research better approaches to creating the digital twins that we work with. So the presentation is going to be split into two sections. So first of all, we're going to cover digital twins, what the anatomy of a digital twin is, how it's used, and kind of what you can get out of it. And then in the second half of the presentation, we're going to be talking about how do we automatically create these digital twins using agentic AI, what problems did we have to solve in order to do that. So yeah, like I just said, we will start with what digital twins are and what goes into them and what you can do. So on the screen here, I have a picture of a digital twin inside of our digital twin editor. Right now, I'm going to talk about, what do we mean by digital twins? What does the industry mean by digital twins? What goes into our specific digital twins and things along those lines. So the best place to start is probably with what the industry means by digital twins. So for anyone unfamiliar, a digital twin is any digital system that can emulate a physical system or any digital system that represents a physical system. Usually representing a physical system is achieved by simulating that physical system. So in some contexts, simulation can refer to 3D simulations or physical simulations. In terms of what we do, we focus on the fault management side of things. So our simulations tend to be injecting failures into the system and trying to map out effectively what symptoms, observable tests, or other components might fail as a result of that failure. And so with that analysis, we can do all kinds of things in terms of real-time diagnostics, prognostics, guided troubleshooting, and resource management. So now that there's probably a baseline understanding of what our models do and what they're meant to solve, we can look at the picture of the model on the screen. The way that we read this is that boxes represent either components that contain failure modes, systems that contain components, or systems that contain systems. Arrows represent functionality that is provided by one system to another. The reason for that is that sometimes the system will depend on functionality from another system, and I'll get into that more later. Circles can be interpreted as tests, where some functionality within the system can be tested by a technician or by a user of the system. There's also a couple of switches here in the top left and top right before the drive test and after the gas tank sub module. Those allow you to configure system state, and things like setups will impact the system state. For instance, when performing a test which requires checking the dashboard lights, you might need the engine on, for instance. And so we would create a setup which says to turn on the engine, and switches let us model that kind of system state, among other things. So if we look at some of the relationships here, we can see that the lights, for instance, are dependent on certain functionality from the driver compartment as well as the engine compartment. Similarly, the wheels are dependent on torque from the drivetrain as well as steering and brake functionality from the engine compartment. The systems are modeled hierarchically. So for instance, if I click into the lights here, we can see that the light system also has its own kind of implementation. And that lets us capture very complex relationships while looking at the system on a micro level. Part of that implementation, if you look at the bottom right, is what we call an AND node, which lets us model out redundancies. Essentially, in this case, both the parking lights can fail independently, and if both fail independently at the same time, this would kind of present the same symptoms as if the parking lights in general failed due to maybe like a fuse failure or something along those lines. So that AND node or that redundancy lets us model out that case. One of the things we can do with effects and tests like this, and symptoms as well, is that we can kind of look at the various sets of failures that would cause the test or effect to be triggered. So in this case, if we pull up the cut set report for the loss of parking lights effect, we can see that there's a certain number of failures, which are cut sets of size 1, which if those failures occurred independently, any single one of them would be able to cause the loss of parking lights effect. Similarly, there's a cut set of size 2, meaning that those two failures have to occur at the same time. And if the left parking light fails and the right parking light fails at the same time, we'll also observe the loss of parking lights. There's also a variety of other reports and analyses that we can do. A couple of them are pictured here. These aren't really comprehensive lists. A lot of the other reports can be accessed through the model canvas itself. This is just kind of two of the drop-down menus that we have for these. Just as an example, the serviceability report will give us a variety of quantitative metrics. If you look at the right side and also the left side, you'll see a few tables containing some of those metrics. At the bottom, we have a couple of charts. I don't want to get too far into some of this stuff because it's a bit of a rabbit hole. But in addition to the serviceability report, we can also generate a diagnostic tree. A diagnostic tree, or a static diagnostic tree in this case, is effectively a decision tree that would let a technician diagnose any given symptom within the system. In addition to static diagnostic trees, we do dynamic diagnostic trees, and we do that through Teammate, a dynamic reasoning engine. What makes it a dynamic diagnostic tree is that users can choose which resources are and aren't available, and you can kind of see that in the image I have here. If you look in the top right of this image, you can see that they can also, when completing tests or setups, choose which tasks aren't doable or aren't performable using the cannot do button. In the left bar, there's a couple of options that would also allow maintainers to modify the various test outcomes of tests that were already performed, the status of various setups that could be performed, the health status of components, whether they're known faulty, known non-faulty, etc., and so on. The reasoner presents them with the most likely causes at every step and aims to perform the diagnosis in a time and cost optimized manner. Like I mentioned before, this isn't really a comprehensive feature set. We actually do a lot more than it would be possible to cover in this amount of time. But really the key point is that once the model exists, the possibilities are kind of endless in terms of analyzing the failure space of the system. So like I just mentioned, there's a lot of information contained in these digital twins and a lot of relationships that need to be mapped. Faults, symptoms, tests, equipment, setups for tests, system state, things like that. The models are very comprehensive and they can really expand pretty quickly for sufficiently complex systems. While our model acts as a single source of truth for any diagnostic related information, it's challenging to build those models sometimes in a time efficient manner. Admittedly, once the model exists, it's extremely computationally efficient to do calculations on it. And we'll kind of talk about some of the case studies where we've been able to show that. So in terms of the question of how our digital twins, or Teams digital twins in particular, built today manually, it is a manual process. Engineers have to read manual schematics, acquire any artifacts they can really get their hands on, and learn the functionality provided by the individual components in the system, and then they have to represent that within Teams. Exports can require manual scripts, and consistency checks require manual review. Additionally, as configurations drift over time, assuming you already have your model done, if the system's updated, you then have to go update your model. This creates an extra ongoing cost in addition to the upfront cost of model development. Now, to be clear, making a Teams model does make sense in a lot of cases, but we believe that if we can cut down on the cost of producing them, that the accessibility would be higher for more customers in more industries with more equipment. So in cases where Teams models were developed, we've had reasonably good success. In a case study involving the F135 engine, the false pull rate for various components was reduced by 17% when using a Teams model, and diagnostic accuracy was extremely high at 97%. It's worth mentioning that 17% is the absolute difference, and the relative factor difference was about a 6x improvement in false pulls. In addition, Teams RT, as well as Teams in general, is used in a wide variety of NASA projects, but in particular on NASA's Lunar Gateway. The system modeled there is extremely extensive, but RT performs extremely well at millisecond scale speeds. That system includes tens, if not hundreds of thousands of components with it. So once the model exists, computation is pretty cheap, but the point of expense is generally in creating the model in the first place. So with that out of the way, we're going to kind of jump into what did we research during this effort to kind of alleviate these problems. So first of all, I'm going to start with the constraints, just so there's kind of a shared understanding of why things were done the way they were. So the first thing is that for these complex electromechanical models, there's generally very large document stores supporting the development of the models. You can imagine these are very technically in-depth systems with a lot of subsystems, each subsystem having numerous pieces of documentation that can be pretty long. So the document stores themselves can be quite large. There's a number of considerations related to how we did RAG and how we processed the documents that kind of arose from that. The second thing is that individual PDF documents could be quite complex in this case. So we have, for these engineering documents, we generally have complex formatting, tables, equations, schematics, diagrams embedded, and some of the older documents are just scanned bitmaps. So we had to create a document processing pipeline that accommodated for all of that. One thing to note also is that because of the layout of some of these documents, you'll generally have procedures which reference a section, and then that section will also reference another section. We had to really support multi-step reasoning in a very complete sense. Finally, citations and human in the loop. because of the safety critical nature of some of the models being developed. And also just as a general practice, it was critical that citations and review were supported, and that if an inaccuracy was found, that somebody could easily go look up the correct information using the citations or using any available tools. So in terms of how those constraints manifested themselves in our solution, we ended up taking an approach where we split the solution into 4 pieces: ingestion, extraction, structuring, and verification. So ingestion was kind of the part where we'd bring PDFs into our system. We would convert them to Markdown, and in that process, we handled those arbitrarily complex PDF documents, as well as the image captioning and storing the metadata for the ingested documents. The second step was extraction, and at this point, we kind of built our knowledge graph. The reason we ended up choosing a knowledge graph was to facilitate the reasoning across the very large document stores. RAG lookups aren't necessarily effective if something like a gasket or a solenoid is referenced a ton of times inside of your document store. But if you're looking for that, gasket or solenoid in the context of a specific other component or a specific symptom, the knowledge graph kind of eased that lookup for the AI agent. So it could find just the references that were pertinent to a specific relationship with another component or with a failure mode or so on. And so the way we ended up facilitating that was by giving the AI agent tools to access the knowledge graph, in addition to just doing these standard, RAG queries for text matching or embedding search and things like that. But on top of the standard tools for information lookup, we also provided tools for traversing the knowledge graph and for querying the knowledge graph. And so that was kind of our method to handling arbitrarily large document stores. Now, on a similar note, once we had that knowledge graph and I was just kind of referencing the tools we had. During that structure step, we did give the AI agent a loop so that it could invoke tools and reason to completion. That allowed us to cover the multi-step reasoning requirement and also provided just kind of a general purpose environment for the agent to collect information about any given problem. Whether that was a very simple problem that required one text lookup or a very complex one that required maybe some fine-grained searching through the document stores. And then finally, our approach to human-in-the-loop citations, in addition to just facilitating human-in-the-loop interactions for document processing and agent interactions, we decided it was very important that the outputs of the AI agent be communicated to the subject matter expert in a way that they could either approve or deny that output. So basically, that just said, hey, we're not going to autonomously generate these models, at least not fully autonomously. So just to go a little more in depth into kind of each step of that 4-step pipeline that I had mentioned, in terms of ingestion, so like I said, we're handling OCR in case of scanned PDFs. We're handling image extraction, table extraction, equations, all of that stuff, links as well. Our goal is basically to do the most high fidelity markdown conversion possible. In terms of what happens after that, we do an LLM repair step. That solves a couple of problems. First of all, it corrects OCR errors. Second of all, it allows us to strip headings and footers that just kind of metadata attached to the document. And we also found that in the case of long tables, if there are footnotes associated with the table, if we pass that whole table into an LLM in a reasoning step, say an AI agent aiming to extract failure modes or something, or DTC codes from a table, if the footnotes aren't near enough to that row, the LLM kind of will neglect them at times. So our solution to this was, during pre-processing, to take those very long tables, split them up into shorter tables and attach the footnotes to each shorter table. And that way, in a future reasoning step, any AI agent reviewing that table would actually have the footnote relatively close to any particular row in the table. And we found that improved the LLM's ability to acknowledge those footnotes and respect them in its generation. Once we have our maximally clean markdown, we create a knowledge map from it. So the way we do that is by taking the text chunk by chunk and kind of feeding it to an LLM. The LLM does have tool access, so it can look at the existing knowledge graph, identify aliases, duplicates, things like that. Also, the developer can specify a schema which restricts the type of entities or the relationships. So, in the team's case, we restrict our entities to tests, components, and a few other team's entities. Our relationships enforce that, failure modes or faults have to be detected by tests, and that faults can propagate to components, and kind of rules that make sense in the context of our knowledge graph or in terms of our problem. We found that kind of helps steer the AI down the road once it goes to query the knowledge graph. And once we built that knowledge graph, it's just a matter of letting an AI agent reason over it, as well as, like I said, performing standard search operations on the document store, like text searches and embedding searches. So from there, once you have an agent that can kind of reason across the document store and the knowledge graph as well, constraint generation can be employed so that you can transform the outputs into JSON or XML for consumption into a software solution. We handle outputs in two formats. First of all, in the plain chat format, there is no constraint generation needed. For consumption in a way that would let us draw onto the Teams canvas, we do need to do a constraint generation step. In either case, we think it's very important that there's a review and an approve deny step. So in that graphical case, where we're consuming the outputs programmatically, we draw the components on the canvas and present the user with approve and deny buttons, allowing them to either approve or deny the generated content. So before I go into the results, I'm just going to quickly explain what correctness and completeness mean. On a query level, that is, say we presented a query to the LLM, like what are the potential failure modes of a battery? In that case, we'd expect maybe two answers, one being battery isn't grounded and one being that the battery has low voltage. In that case, we would say that correctness would be the number of responses which were expected. So an incorrect response would be the inclusion of some hallucinated failure mode, like the battery doesn't have fuel. That would be an incorrect output, whereas an incomplete output would be neglecting to include one of the two correct outputs. So if it came back and said that the battery isn't grounded is the only failure mode, but it didn't specify that the low voltage could also be a failure mode, that would be a 50% completeness. For the more well-versed statistically, you can just think of completeness as type 2 error and correctness as type 1 error. So with that said, I can kind of jump into the results. A little background, we had tested 100 queries at 3 trials each. The mean correctness and completeness were 92% and 91%, and the lower 95 percentile confidence balance for both of those were 90% and 88% respectively. Both of those exceeded the subject matter expert in terms of completeness and correctness, which were 90% correctness and 82% completeness. In addition, we observed an 85% reduction in engineering hours, specifically when submitting the queries sequentially. If we submitted the queries concurrently, the engineering hour reduction was much higher, around 95%. On the left, we have a couple of charts. The left shows the time comparison of manual lookup versus agentic AI lookup for a variety of queries. The right chart shows a radar chart of the correctness, completeness, and the inverse time to completion normalized between 0 and 100 for manual lookups, the AI agent, and using the AI agent in a parallel fashion. One thing I'll say that's not noted on the slide, we did do a couple tests on different workspaces that weren't standard engineering document stores. For instance, we created a help chatbot for our software using user guides as the supporting document store. The results were fairly good. In addition, we observed a few cases where the AI agent would come back and ask for clarification on the user prompt. In those cases, we considered completeness to be 0% because it didn't return with an answer, and we considered correctness to be 100% because it didn't present any incorrect answers. In terms of our takeaways, we kind of already knew that our architecture for digital twins and digital causal fault models is very scalable. Our goal is to kind of solve the knowledge acquisition problem, and based on the results on that, we feel like we've done pretty well. At this point, we've shifted, at least in our benchmarks, the human efforts from being information retrieval, lookup, and reasoning to being a validation and review step. Our next plans for this are kind of going to be to trial it on more projects, commercialize, and in that process kind of resolve some of the compliance things that need to be sorted out in order to offer this to certain entities. But yeah, thank you for listening. Thank you to the Air Force and the Army for sponsoring our efforts. Thanks everyone from QSI for your efforts, in particular Dr. Patty, Stipto, and Chris Norton. And yeah, have a good day.